As a part of our geotechnical engineering series, in this video, we will look into retaining walls and why they fail. Watching our previous video first may be helpful to better understand some of the concepts presented here. In short, the previous video showed that soils always fail by shearing, or in essence, sliding. Therefore, in general, we as engineers are mostly interested in the shear capacity of soils. However, the shear capacity is influenced by the confining stress, so we needed a more complicated model rather than just looking up a single value. We looked into the so-called Moore-Column model. This model is described by the friction angle as the single most important parameter that determines the strength of granular soils. The physical meaning of the friction angle is related to the incline at which the soil slides. Keep that thought in mind because it is absolutely crucial for retaining walls, as we will see soon. In this video, we will focus strictly on gravity retaining walls, which are the most common, but just for completeness, be aware that there are several other types of walls, including cantilever, crib, buttress, sheet pile, tied back, and several others. Soil reinforcement is also a very popular design solution lately. Soil reinforcement, or mechanically stabilized earth, is achieved by extending polymer reinforcing strips or other kinds of meshes into the retained soil. All these types of walls have one thing in common, which is to retain the earth behind them. The retained earth behind them is therefore, understandably, the largest load that they have to resist. This load manifests itself into a sliding action or overturning of the wall, which are the main two failure modes. Other modes of failure are also possible, but they fall under stability or foundation failures and will not be investigated here, but in some of the upcoming videos on foundations and slope stability. If you're enjoying these videos, consider writing a comment or clicking the like button. This helps us greatly. Now, on to the design considerations. The design of retaining walls can be approached from two directions. Either increase the resistance of the wall or decrease the earth pressure. Let us first look at the resistance side, since it is fairly simple. Gravity walls use their own weight to retain the soil mass. The weight of the wall induces a frictional force at the bottom of the wall that prevents sliding. Embedding the wall into the ground can add an additional component of resistance, which helps greatly. Extending the base of the wall into the backfill helps activate the soil mass as part of the wall and increases the base friction and resistance to overturning. But this usually requires more excavation and could increase the cost significantly. Alternatively, increasing the size and therefore the mass of the wall could do the job, but this is also a costly solution. In practice, engineers tend to pay more attention to the soil behind the wall and reduce its effects. Soils act similar to water in the sense that they exert pressure on its surroundings. This pressure increases with the depth of soil. Unlike water, the pressure from the earth depends on whether the wall can move or not. In almost all practical cases, the wall does move, and this helps relieve some of the pressure applied against it. Terzaghi, the father of soil mechanics, performed a bunch of full-scale tests on retaining walls and found that even the most insignificant wall movements in the order of a fraction of a millimeter could reduce the lateral earth pressure applied to the wall by 50%. Theoretically, this reduction has to do with something called the active loading case and is related to the coefficient of lateral earth pressure. But instead of going into technicalities, we will try to explain this intuitively. When the wall moves, the soil wants to follow it and it starts to slide or separate from the main soil mass. We saw this in action in the previous video. This separation helps us because the detached soil wedge has less mass and exerts a lower pressure than before the wall moved. Just to be clear, this movement is not visible by the naked eye. If you can visually see that the wall has moved, then you're probably looking at a failing wall rather than the active loading case. So here you can see how increasing the friction angle of the soil decreases the pressure exerted on the wall. Now, a good question is, how does one increase the friction angle? The friction angle is intrinsic to the type of soil. For example, clays and silts have low frictional strength. They use their cohesion or stickiness to carry the loads. The cohesive strength is unreliable because it could sometimes disappear if the soil gets saturated. Besides, Clays and silts have low porosity and tend to trap the water, which is not something you want behind your wall. Granular soils like sands and gravels make for the best backfill material. They have decent friction angles and high hydraulic conductivity, which allows the water to easily drain. But to get the best out of your backfill, it is absolutely crucial to have the backfill densely compacted. As we saw in the previous video, compacting the soils packs the particles tightly together, which significantly increases the friction angle and therefore the strength of the soil. If the gravel is also well graded, meaning the size of the particles is fairly uniformly distributed, then the strength is even better. The last point to make before moving on to the actual wall scenarios is about drainage. Providing drainage to the wall is probably the most important consideration. The effects of poor or no drainage will become apparent shortly. Now, let us look at a retaining wall design scenario and see how the soil parameters affect the factor of safety. If you're not familiar with the concept of a safety factor, it basically means how much the resistance of the wall is bigger than the driving force of the soil. A safety factor of 1 means that the two forces are equal and only a minor increase in the weight of the soil will cause a collapse. The investigated wall is to resemble a typical wall often seen in residential areas. The model case does not consider any surcharge loads on top but only the weight of the soil. 4 different scenarios of the same geometry were considered. First, the soil was assumed to be densely compacted, resulting in a high friction angle. The second scenario used the same soil as the first, but with geogrid reinforcement added to the soil. The third scenario considers the same soil but no drainage to the wall, so there is a buildup of water behind it. And the last scenario assumes a loose backfill material with no compaction and a lower friction angle. After running the analysis in Optum, the following safety factors were obtained. Unsurprisingly, the reinforced soil achieved a safety factor of 2.9, which means the system is nearly 3 times stronger than the equilibrium condition. Let me know in the comments why do you think that is. The case with no drainage achieved the lowest safety factor of only 23% higher than the state where collapse starts, and is also 75% weaker compared to case number 1. The loose backfill also performed poorly, but still outperformed the wall with poor drainage. The topic of proper drainage and construction of retaining walls have so much in them that is impossible to cover here. Let me know in the comments if you would like a part 2 to this video or whether to move on to other applications such as foundations and slope stability. Or if you're too lazy to write, just click the like button as a sign of support and we will keep producing more videos. Thanks for watching and see you in the next video.